All right, let's begin from where we left off in the last class. In the last class, we were talking about adders, specifically the simplest form of an adder, ripple carry adder. For this ripple carry adder, I have shown you two topologies. Okay, first one is based off a regular 1-bit full adder. Okay, that looks like so. Okay, a regular full adder has all of these inputs. Okay, A, B with the inputs. This is an adder, and then there is this sum, and then there is the carry out. Here is the carry in, right? So this is 1-bit full adder. If I want to implement a 4-bit full adder, all I have to do is to do this. Okay, all I have to do is to cascade 4 of them to implement a 4-bit adder. Okay. Now, when I make these connections like so, okay, I have my 4-bit adder. This is A1, B1, A2, B2, A3, B3, and A4, B4. I'm going to call this Cin equals to C0. Okay, Cin is the same as C0. This is C1, which also propagates to C2, and then on to C3, and then the output carry C out is the same as C4. Like I mentioned, Cin equals to C0. Okay, so I'm trying to add A1, A2, A3, and A4 with B1, B2, B3, B4. Okay, so this is the 4-bit adder. Okay, 4-bit ripple carry adder. And I mentioned that this path right here, from carry in all the way to carry out, okay, from carry in all the way to carry out is called the critical path. Now, in order to slightly improve this path, what I have done is to implement a mirror ripple carry adder. So ripple carry adder configuration 2 based on mirror adder. Mirror adder is a slightly more efficient adder configuration. Okay, so it's a slightly more efficient adder configuration. This guy still has 4 inputs. Okay, this still has 3 inputs and 1 output. Okay, 3 inputs and 1 output. That are like so. Okay, 3 inputs and 1 output that appear like so. So here is the adder. This is A input and B input. What you want to remember is that you have sum complement and carry complement coming out of this stage. Okay, as long as I'm inputting and doing C0 carry in. Okay, so if I want to implement a bunch of these adders or a 4-bit adder, what I have to do is this guy. Okay, then I duplicate that. I'm trying to build a 4-bit adder here. Okay, so this is 4-bit adder. The bits appear like so: A1, B1, A2, B2, A3, B3, and A4, B4. So this is sum 1 complement. So in order to get sum 1, we have to pass it through an inverter. So that gives us sum 1. This guy is C1 complement. That's the output of the mirror adder. Okay, so in order to get a in order to do this, what we have to implement is we don't have to invert this guy. So if we pass in inverted inputs A2 and B2, the output here is going to be S2 in its uncomplemented form and C2 in its uncomplemented form. Okay, so A3 and B3, you pass them in uncomplemented form, and then this gives you your S3. Okay, then you have to do that. As you know, this guy C3 is going to be complemented, and then the sum here is going to be S4. This guy is going to be C4. So the idea is this. If you look at even stages, stage number 2 and stage number 4, the outputs corresponding to these stages are regular. They're in uncomplemented form. Okay. On the other hand, if you look at the even stages, this guy and this guy, the outputs corresponding to them, so there is S3 complement here. So the outputs corresponding to those odd stages are uncomplemented or complemented. Okay, so the idea is this is a bit more efficient owing to the fact that you implement sum from the complement of sum can be expressed as a function of carry out complement. Okay, and in the last class I have shown you that 1-bit full adder, mirror adder, uses fewer transistors and is a bit more efficient. It reduces the delay. Also pay attention to this. All the even stages shown in blue here, they have complemented inputs. Okay, even stages have complemented inputs. Okay, so when I do that, when I pass complemented inputs, the resulting outputs are uncomplemented. So that's the architecture topology of a ripple carry adder based in mirror adders. So each of these configurations is a mirror adder. Now, the really cool thing about mirror adder is the delay in this critical path is reduced. The delay in the critical path is reduced, but don't forget that you introduce additional delay, okay, in creating these complements or in inverting some complement back to some. So what you're doing is you're reducing the delay along the critical path and passing the delay on to the um, off critical paths. You're passing it off of critical paths. That is fine as long as I reduce the delay along the critical path. I can tolerate a bit more delay off of the critical path. Okay, so that's what we are doing here. That's the advantage of mirror adder based ripple carry adder. Okay, nevertheless, it's really inefficient for C4. Okay, C4 is really waiting here for C3, which is in turn waiting for C2, which is in turn waiting for C1, which can be generated from C0. Okay, so we have to find, and there are many topologies which break that dependence. C4, if you can express C4 as function of A4, B4, A3, B3, A2, B2, A1, B1, and C0. Then what you have done is this dependence of C4 on C3 has been broken. You don't have to wait for C3 to calculate C4. And that's the idea of carry look ahead adder. Okay, and that will be the topic that we discuss in today's class, carry look ahead adder. Okay, in order to understand the concept of questions so far, what questions do you have so far, please? Okay, so we are going to discuss about carry look ahead adder. Okay, carry look ahead adder. If you remember, I defined a few terms in the previous class. Propagates, P, generates, G, and kill terms. Propagates is defined as A XORed with B. Okay, generates is defined as A times B. Kill is defined as A naught times B naught. Okay, so you can define generates, propagates, and kill for each of these stages. Okay, let me clear this up a little bit. Okay, so if I want to calculate the propagates for this stage P3, I can very well do that using A3 XOR with B3. If I want to calculate G4 here, I can calculate G4 to be A4 times B4. Okay, similarly, I can calculate P4 as well. I can calculate K4. I can calculate G3 as well as a function of A3 and B3, so on and so forth. So for each of these stages, I can calculate P, G, and K. So if I take any stage I, Pi, then AI plus Bi is the propagates. Generates of stage I is AI times Bi, and the kill is AI Bi complement, AI naught times Bi naught. Okay, so what we want to notice is that these terms G, P, and K are independent of carry M. So there is no carry term when you want to calculate these terms. Okay, so I can use them to implement this. So the idea of carry look ahead adder is to implement something like this. In order to calculate any carry I, okay, so let me write it out here. Any arbitrary carry I want to express it as a function of all the independent variables AI through 0, Bi through 0, okay, and carry in, which is the same as carry 0, okay. Earlier ripple carry adder was a function of AI, Bi, and Ci minus 1, okay. In order to calculate the carry of a stage C4, I had to wait for C3 to come. This is a bad design. I don't want it. So there's a lot of delay. But here, this is carry look ahead, because there is no C3 term here when calculating C4. C4 can be directly expressed in terms of A4 to 1, A3 or B4 to 1, okay, or B0, B4 to B0, and of course C0, carry input. There is no C3 term here, okay? There is no C3 term over here. So that's a better design. This has a lesser delay. Okay, so that's the idea. It only makes our circuit more complicated, but that's fine as long as it saves me a lot of time. Okay, C4 is dependent on A4 to A0, B4 to B0, and C0. It's not waiting for C3. Okay, so that's the idea of carry look ahead adder. Let me see how I can calculate that. Okay, so the idea is based on developing a carry chain, breaking the carry chain. Okay, as we know, if we want to calculate C1, okay, if I want to calculate C1, then what I have to do is to do G0 plus P0 times C0. Okay, so in other words, if these are A0, A1, B1, B2, so instead of this guy, so I'm trying to add A0, B0, A1, A2, and A3 is a 4-bit number A. There's another 4-bit number B, which is B3, B2, B1, and B0. Okay, C0 is the input carry. We know by definition C1 is G0 plus P0 times C0. That's the definition of carry. Okay, so if you want to calculate C2, okay, C2 is defined to be G1 plus P1 times C1. Okay, if you want to calculate C3, that is defined as G2 plus P2 times C2. Okay, so these are the expressions for carries. Let me copy them here. Okay, carry. So this is a regular carry. And what if you want to improve this? So carry. And this is the dependence you want to break. You don't want C2 to be a function of C1. Even so, you don't want C3 to be a function of C2. So look what I'm going to do. I'm going to start with bottom, or I'm going to start from top down as well. So I'm going to leave C1 to be G0 plus P0 times C0. Okay, now I'm going to make a modification to the next equation, equation number 2. Okay, equation number 2, what I'm going to do is C2 is G1 plus P1 times, in place of C1, in place of this C1 over here in equation 2, I'm going to replace it with G0 plus P0 times C0. Okay, the same thing. So this comes out to be G1 plus G0 times P1 plus P0 P1 times C0. Does that make sense? Can anybody tell me what is the use of doing this? It seems like I'm complicating my circuit. Why would I want to do this equation? Okay, think about this. Compare, when you compare these two equations, okay, the ones that I'm going to highlight now. Okay, these two equations, compare these two and tell me why one is better than the other. Why especially this guy is used as a carry look ahead adder.
Because you're not waiting for the carrying of C1.
Correct. Thank you. So in this equation here, C2 is a function of G1. G1 is simply A1 and B1, right? So G1 is A1 times B1, right? So it's a function of, so carry 2 is a function of A1 and B1 plus A0 and B0, okay? And also it's a function of A1 and B1 because of this guy, okay? Then A0, B0, and C0, okay? As opposed to this guy, the one on the top, where C2 is a function of A1, B1, and C1. C1 is in turn a function of C0. So I'm breaking this dependence. If you remember, if you go back to the discussion I made earlier in just a second ago, just a minute ago, I said I wanted to break this dependence. Ci depending on Ci minus 1 is a bad thing. I don't want that. I want Ci to be dependent on C0 only, and A1, AI through 0, BI through 0. That's exactly what is happening. As a matter of fact, why don't I copy this? Okay, just so you can see what exactly I'm talking about. So if you remember, this guy, Ci, the top equation, has lesser delay. So this guy, Ci, okay, where I is 2, depends on A1, A0, A1, A0, B1, B0, okay, and C0. It is not dependent on C1. That's the sweet thing, okay? So the idea that you don't have to wait for the previous stage carry C1 is the advantage here, okay? So this is carry look ahead configuration. But you notice that it's a bit more complicated. There is more AND gates and more addition circuits needed to implement that. But that's fine. If it saves me more time, there are applications where speed is more important than power consumption. So let's do C3 as well. C3 can be expressed as G2 plus P2 times C2. Okay, C2 can be expressed as C3, carry 3 can be expressed as G2 times P2 plus C2. But again, here is the dependence I want to break. I can't tolerate that C2. Okay, I can't see that C2. So I'm going to have to break that up. I leave this G2 as is because G is independent of carry. Remember? G, P, K are independent of carries. Okay, so I can tolerate that. I can pretty well tolerate any amount of G in my expression. So G2, I can leave P2 as is, but C2, I'm going to replace that with this equation here. Okay, I'm going to bring that equation over there. So let me do that. Okay, carry look ahead adder. So I'm going to copy this equation here and paste it as is. Okay. So I can expand this out. I can expand this out to look like C3 is a function of G2 plus P2 times G1 plus P2 P1 times G0 plus P2 P1 P0 times C0. Okay, so what you want to notice is again the exact same thing. Okay, the idea that you can express a carry in terms of AI, BI, and C0. Okay, and not on AI minus 1. There is no, if you notice, there is no C1 term. There is no C2 term. You're expressing C3 as a function of carry not A3 or A2 to A1 and B2 to B1. So this is a good thing that I'm not waiting for previous stage carry. Okay, so this is the idea of carry look ahead adder. Okay, carry look ahead adder. The reason is I can't tolerate C2. Well, initially I began with C2, but I eliminated that by incorporating more and more look ahead logic. Okay, that's the idea of carry look ahead logic. Questions, please. Okay, you can extend the same idea further. Okay, you can extend the same idea further to generalize the notion of G, P, and K for groups of bits. Okay, you can generalize the idea of G, P, and K for groups of bits, and you can come up with many creative ways for looking ahead. Group generates, group propagates, for generates for groups for bits 8 through 2, for example, can be expressed as generates for 8 through 4 plus propagates 8 through 4 times G3 to 2. So something like that. So you can break down, you can express generates, propagates, and kill terms for groups of bits taken together. And then you can look ahead the carry for those groups of bits. And then there's a whole theory behind how you can do that. But we'll not dwell too much on it. Okay, I have given you a pretty good introduction to carry look ahead logic. Okay, carry look ahead logic, which generates the carry independent of the previous stage carries. Okay, that's the idea of carry look ahead, and we leave it there. We move on to talking about other arithmetic circuits like 1 and 0 detectors, so on and so forth. Okay, 1 and 0 detectors, other interesting stuff. So let's start with comparator circuits in the first place. Okay, compare. So questions so far, please. Okay, comparator circuit. Let's say I have 4 numbers. I have 2 numbers, A and B. Each of these is 4-bit numbers, A0, A1, A2, and A3, B0, B1, B2, and B3. Okay, each of these is 4-bit numbers, and I want to compare A and B. So I want to build a circuit that takes these two as inputs, A and B as inputs, and then generates a term, Z, only if A equals to B. Okay, and then generates another signal, okay, called C. If this C is 1, that means A is less than or equals to B. Okay, and if this C is 0, then that should imply that A is greater than or equals to B. Okay, that's what it should imply. It should greater than B, greater than or equals to B. So the idea is this: how can I build a comparator circuit? A digital comparator circuit. Okay, so it's rather straightforward to build a comparator circuit out of adders and inverters, and this is what I'm going to do. I'm going to show you the schematic for exactly that kind of circuit. Okay, let's start with an adder here. Okay, that's an adder. Okay, that guy. Now let's see. So what I'm going to do is I'm going to pass one of the inputs in its uncomplemented form. Okay, that will be B. And I'm going to invert one of the inputs here. I'm going to invert A actually. And I'll show you why that is that makes sense. Okay, why I'm doing what I'm doing. I'll show that to you in a second. Okay, so let's just say that's just for one bit. I want to duplicate this for a second bit. Okay, and then implement the exact same configuration for the remaining 2 bits. So this guy is A0 and B0. This is A1 and B1, A2 and B2, A3 and B3, right? So the term that is the output that is coming out of the adders here is the sum term. Okay, so this is the sum 3, sum 2, sum 1, and sum 0. Okay, and what I'm going to do is to pass them to pass them through AND gates. Let's see, I'm going to invert them and pass them to AND gate. Okay, I'm going to invert them and pass them through AND gate, something like this. Okay, so let's see, these are AND gates, and I'm going to call this as C carry. And my claim here is that this term Z, this implements Z, and this implements the C term. Okay, so if you think about it, I mentioned that I want to implement a circuit that has 2 outputs. Okay, the output should be C and Z. Sure enough, the outputs are C and Z as well. And the input should be A and B. The input should be A and B. Sure enough, the inputs are A and B here. Okay, and then the idea that what I'm going to do with the input carry here is I'm going to pass it to power supply VDD. And I want you to think about what exactly is being done here. Okay, this has 2 inputs, sure, and it has A and B inputs, good, and 2 outputs, C and Z. And why is it, how does this implement a comparison circuit? Okay, well, you have to realize that in order to compare the terms A and B, I can do them by implementing a B minus A function. Okay, I want to implement a B minus A function. When I implement a B minus A function, if the result is 0, then this Z term is going to go to 0. Because see what I'm doing? I'm inverting A term and adding a 1. What is that? I start with A3, A2, A1, and A0, right? And then I'm passing them through an inverter. Each of these bits, a bitwise inverter, produces A0, A2 naught, A1 complement, and A naught complement. What is this guy? If you remember, if you think about it, that's the ones complement. If you do the bitwise inversion operation of a 4-bit number, that's its ones complement. How do you get the 2's complement out of this? You simply have to add 1. Okay, so in order to get the 2's complement, I'm adding a 1 here in the form of a carry. Okay, so once I get the 2's complement, I know, so it's 1's complement, A3 naught, A2 naught, A1 naught, and A naught plus 1. That's the 2's complement. So B plus negative A, that's the operation I want to do. B plus negative A is nothing but a 2's complement. Okay, so I'm generating this 2's complement number by generating the 1's complement and then adding 1. Okay, so that's exactly what I'm doing by implementing the inverters here. Okay, so as you can see in the color coded scheme, the inverters plus the VDD, that gives you the 2's complement. Okay, that gives you the 1's complement plus 1. Okay, that's the 2's complement or the negative of A. Okay, so take an example here. Let B equals to 111 and A equals to 100. So you're trying to subtract 7 or subtract 4 from 7. Then if you follow this, you'll end up with 111, which is 7, and the 1's complement of 100 is 011. You add 1 to it, it's going to be 101010. So when you do this, when you try to add these two numbers, okay, what happens is you end up with 1, 1, and a carry of 1 and 0. Okay, so this 100 is the 2's complement of 100. It just so happens that 100 is the 2's complement of 100 here. So whenever there is a carry, that implies that number A is smaller than number B. Okay, that's the point I'm trying to drive home anyways. So if there is a carry signal here, a carry signal here signifies that A is less than B. Okay, as we just saw in that example. Okay, when A is less than B, there's going to be a carry signal when you do B minus A. Okay, so that's the fundamental logic that we are trying to understand here. Okay, so the idea, you can now elaborate this further and tabulate the idea of unsigned comparator. Unsigned comparator. All the circuit is doing is to implement B minus A in the form of B plus 2's complement of A. Okay, and as we saw in the example, if A equals to B, then the Z term in unsigned comparator, the 0 term is going to be 0. Okay, and you can evaluate why that is the case. The 0 term, this guy, that goes to 0. Okay, now if A is less than B, Z term is not going to be, did I say it wrong? Z term will be 1. Okay, when A equals to B, Z term will be 1. When A is less than B, Z will be 0. And more importantly, there will be a carry signal. So signifying that I have C. If A is greater than B, then C naught is going to be 0. And then Z naught is going to be 1, or Z is going to be 0. And then you can elaborate this. If A is greater than B, what happens? C naught plus Z. If A is less than or equals to B, then you have C plus Z, so on and so forth. Okay. So that's the idea of unsigned comparator. Unsigned comparator outputs. Questions, please. What questions do you have at this point?
Professor,
Yes.
I'm having a question. Like, I didn't understand how you generated the 2's complement by using an inverter.
Yeah. Let's say you pick a number. A is 1001. How do you generate the 2's complement of it?
I'll invert
Well, you
that
start.
and then add 1.
You invert the 0, 1, 1, 0. You perform a 1's complement first by inverting each of these bits and then adding a 1, you have 2's complement, right?
Yes.
So A0 should become A0 naught. A3 should become A3 naught, correct?
Yes.
That's exactly what this inverter is doing. This A0 will be made A0 naught.
Yeah,
This
but
A1,
that's the one complement, right? How is it generating
correct.
2's complement?
Don't forget this guy. The one being added here through the carry in. This is a full adder, right?
Oh,
So when
okay,
I
okay.
add a 1 here, that generates a 2's complement number.
Okay.
Does that make sense?
Yeah.
Okay, so that's a good question.
And also,
Other
one more
question?
question. Like when
Yeah.
A is equals to 0, can you
Okay.
move a little downwards, like the slide? Yeah. So when A is equals to 0, Z is equals to 1, you said, right? But I think
No, I said
it must be equal to,
when A is less than B.
no,
When A is
first
less than,
case, like when A is equals to 1.
when I the first case was when A equals to B.
Sorry, yeah, A equals to B.
Correct.
So I
So when
think
you
that
do,
Z would be equals to 0 at that case.
it could be. So the idea is that when you're doing A equals to B, all of these terms, so all of these will become zeros. Okay, this is going to become a 0. This will become a 0. This will become a 0, and this will become a 0. And each of these at the input of the AND gate become 1, and then you will end up with a 1 here. So this Z term, when that goes high, that means the all the bits are equal.
Okay.
Okay.
Like I was thinking, like if we are in, if A is equals to B,
Okay.
then
So let's add two numbers. 1010 is B, and I'm trying to subtract 1010 over there. Correct? So in order to do that, I have to generate 0101 and add a 1 to it. It becomes 10110. Correct? So this is 2's complement of A. So
yes,
add 1010 to 0110. Okay? Then what happens is there's a 0 term over here, 0 over here, 0 over here, 1 0. So the 0, all of these terms become 0. Does that make sense?
yes,
Okay. So I can change this. I want to change this guy to C plus 0. See, there is a carry term, and then there
yeah,
is a 0 term that becomes 1. Does that make sense?
yes, yes. It makes sense now. Thank you.
Yeah. Other questions, please. All right, I'll see you folks back on Tuesday then. So let's see something in the chat. It's cumulative. There'll be study guide for the final, and will the final be cumulative? Thank you. The final will be cumulative, the final exam. About 60% or 60 to 65% will be from material after midterm, and 40 to 35% before midterm. And I'll provide a study guide sometime this weekend. Other questions, please. Okay, we'll see you folks back on Tuesday then.